Hello, in this lecture we are going to prove the before mentioned Riemann mapping theory. So here let's assume that omega is a simply connected domain in C different from C. Without the loss of generality, we can assume that 0 is not in omega. Otherwise, we can assume that translate omega such that the missing point, a missing point is translated to 0. So if you draw a picture, so you have missing point at the origin, and since omega is isolated, at least you have a path go to infinity. That's the intuition. Okay, so the Riemann mapping theorem claims that so if z0 is in omega, then there is a unique conformal map f from omega to d such that f z0 is 0 and f prime 0 is greater than 0. I should say here is 1, 2, 1 and onto conformal map go this way. Okay. So let's do a remark. Actually here the uniqueness is kind of straightforward, because suppose you have f1, f2 satisfy the same relation, then f1 inverse, f2 compose f1 inverse is an automorphism of D, and the derivative at the origin is greater than 0. But since we have the classification of the map, and we know that the derivative at 0, also fix the origin, then we know the map must be exponential ei theta times z, and therefore the derivative is exponential I theta, so theta can only be 0. Therefore f2 compose f1 inverse is the identity map f2 equals f1. So the uniqueness follows easily. The really difficult part and the essential part is existence. And there's a remark too, there's a related theorem which is called uniformization, which is also known to Riemann, but then proved by Kobe and Hilbert. of course, Dirichlet also contributes a lot, but he proved based on the so-called Dirichlet principle to prove it. But Dirichlet principle only proved until Hilbert's work. Actually, in that work, Hilbert introduced Hilbert spaces, a very important concept. Okay, so uniformization theory consider not only simply connected domain, but all the domain, and also even more consider the one-dimensional, let S be one-dimensional complex manifold. So here, complex dimension. And then there exists a holomorphic locally invertible maps from C to S or CP1 to S or D to S. So actually from the previous the first two, so let's make first two cases, then we conclude actually more. So in first case, S either biholomorphic to C or S biholomorphic to C quotient discrete Z. So in that case, you have a stripe so the map just identify at all the points with one period, so it's a one period function. It's the same as C plus omega in S. So you glue from the picture, you glue the blue line with the red line. Blue line glues red line. Okay, and also this is one period function, and also you have the possibility, which is two period, and as we showed before, then this will be torus. So you glue the blue line with the red line and glue two colorful lines. Okay, and if S is, for the second case, S is just the CP1. Because CP1 is simply connected, you cannot take quotient. If you still want the quotient space is smooth, and then most difficult one, complicated one is the last one. S is quotient of D by a discrete group. D is a discrete group of PSU11 or if you use a up half plane model, or equivalently the discrete group PSL2R. So if you draw a picture, then probably you will have so how to draw. This is one of the example. So you glue together the yellow line with the green line. And I will not specify the group carefully, so you can check Katalog's book. If you have interest, it's called Furcation Groups. So if you have interest, please select some topic from from his book and do some reading report. Last year we had a student doing a good report on this, so at least it's doable. Okay, and so our idea is, so now let's look at the proof. So our idea is we want to first so this is the domain. It's unbounded at the very beginning. We want to put the domain into disk at least. Into disk biholomorphically. So biholomorphic map into D. And then next step, since our ultimate goal is to make the map the whole disk, then we want to enlarge the image in the disk as large as possible. Enlarge the image in D as large as possible. So that means we try to expand the image and we can conclude that finally you can find some map just the whole disk. So there will be two steps. Step 1, from the proof, you will see it's relatively easy. Step 2, we need some very fundamental idea from Montel. Just like take the limit of holomorphic functions, and then you want to prove something large, the existence or minimize the kind of. So proof let Fz be a branch of the square root map defined on omega with the other branch being negative Fz. That is Fz squared equals z. So let's recall how to do this. We can define Fz equals exponential 1/2 cos 0 to cos integrate of 1 over cos d cos. Okay. So here is the for all z in omega. Since omega is 0 is not in omega, and omega is simply connected, Fz is well defined. There's no ambiguity. So actually, if you want to state this in a theorem, then probably you can look at your book. It says if omega is simply connected so any primitive so there is a primitive Fz there's a branch of log z well defined on omega. You just use the same proof. In other words, here you don't need to do any cutting. You can define omega on the whole domain. You can define the function log z on the whole domain. Okay, then we claim the following. First, Fz is univalent on omega. Proof. This is because if it's not univalent, then let's do this. For all z1, z2 in omega, if fz1 equals fz2, then you square it. z1 equals f squared z1 equals f squared z2 equals z2. So we are done. We prove the univalence. And claim 2, we want to show that f omega, the image of omega and f, and the image of omega and negative f. Notice that negative f is the other branch, so it's empty. So proof. So if there exists z1 in omega and z2 in omega such that fz1 equals negative fz2, then you also square it. you have z1 equals fz1 square equals negative fz2 square, which is z2. And then you plug in, you find fz1 equals negative fz1. Okay, then fz1 is 0. But by definition, 0 is not in omega. Then we derive a contradiction. Hence, at the very beginning, the intersection is empty. And thirdly, there exists B in C and omega greater than 0 such that f omega intersects the ball is empty. If you draw a picture, this will be very clear because in the map, f omega might be some region, it might be unbounded. And the other branch, f inverse omega, also takes some part of the domain. And then, of course, prove by openness of holomorphic maps, negative f omega is open. So this is the blue part. It's open in C, and therefore we can take a neighborhood or an open ball. Z minus B less than R, such that, so where I is greater than 0, such that f omega intersect the ball is empty. Okay, now define GZ equal to R divided by FZ minus B. And then it's clear for all Z in omega, GZ, the norm of GZ is less than or equal to 1. Sorry, less than 1. So in other words, G omega is contained in the unit disk. So we are done the first step, proof of the first step. Okay, now let's look at the second step, step 2. So now we fix a point. So without the loss of generality, next we assume that omega just inside the unit disk. And we take a point P0 in omega. Consider all the holomorphic maps such that maps omega still inside the unit ball be the set of all univalent functions from omega to D such that P0 is mapped to 0. And we want to, so our final map, the unique map, maps onto the disk should be inside this family. So our candidate is inside, but the problem is how to pick it out, how to characterize it, so that it's distinguished, so that we can distinguish with it with all the other maps. So we need to have some characterization or quantitative property. So we will pick out a special one, F in Mescal F such that F from omega to D is a biholomorphism, 1-to-1 onto holomorphic map. So 1-to-1 onto holomorphic. So the idea is consider the derivative, the norm or derivative at the origin, at the point P0. P0 is not important. You just fix one point. And actually, if you look backwards from the Schwarz lemma, then you will see the derivative at each point, if it's automorphism of the ball, achieve its largest possibility value in magnitude. So we define mu to be supremum of the norm or derivative at the point P0 for all f in Ker f in the family. So next we will prove the following proposition. Exists f in the Ker f, the family, such that the derivative, the norm of the derivative equals a maximum. So let's make a remark. So this is kind of the existence of certain minimizer. The idea will be also used in proving the uniformization theorem. But then the problem is more difficult because there we need to minimize a certain integral, which is called Dirichlet integral, similar to some energy functional. Okay, then how? So for that, there will be some function of f, and in some domain omega, d, for example, dx, dy, or dz norm square. So you want to take the infimum of all the f in some space, so let's call it M. And the question is, we want to show that there is a function f0 in certain family such that the integral taking at f0 equals infimum. So that's called the minimizer. Okay, but this is not easy to prove. This is called by Dirichlet. It's a Dirichlet principle. He just claimed that there exists such F0, but didn't prove it. So the proof only given after the work of Kolbe and Hilbert. In particular, Hilbert introduced the concept of the famous Hilbert spaces to solve the existence of the minimizer of the Dirichlet functional. If you have interest, I suggest the book of Siegel, the complex analysis. So I can't remember the full name, but he has a 3-volume textbook, and this will be either in the first volume or the second volume. So if you have interest, I strongly suggest you to read Siegel's book. It's fantastic. And the most important part for his book is that he just followed the original proof due to Hilbert, Kolbe, Poincaré. So you will see it's very old-fashioned, but tells you a lot more than the current proof. Current proof, we usually use the PDE method. It's not that intuitive. So I would say in his book, he also showed that to show that the map is 1-to-1, Poincaré introduced his index theorem. So intersection index, so what does it mean? It's a topological concept, and it's very important. Okay, I will not take too much time on this. Let's just prove this. Okay, since norm of f is less than 1 on omega, so for f in omega, it follows from Cauchy's formula for the first derivative of a holomorphic function that supremo of the derivative norm, the magnitude of the derivative is bounded by some constant ck for any compact subset k or omega. This means that so we first take a sequence of compact sets, subsets, K1 inside K2 inside K3 inside omega, such that the union of Ki is omega. And the above estimate tells you the family of functions in F is equicontinuous. therefore, by a diagonal method, so how to apply diagonal method? So please look back to Math 521. For any sequence in capital F exists a subsequence we can use diagonal method just a little bit later. We first show that for any sequence in F, there exists a subsequence which converges uniformly on compact subsets to a limit function on any compact set. So here the equal continuous is on Ki, on compact set Ki. This is because of the equal continuous. So you can use Archela-Ascoli theorem to prove this. If a family of functions is equal continuous, then you can find a subsequence which converges uniformly to a limit function. And then since this is true for all the compact sets, but the family might be different. So by a diagonal method, we can conclude for any sequence in F, we can find a subsequence which converges to a limit function on omega, and the convergence is uniform on any compact subset. And now take F1, Fn in F such that the limit of the derivative of Fi at Pi norm goes to infinity. This is mu. You take a sequence of functions approximate the maximum magnitude of the derivative at point P0. Then by the previous argument, we can take a subsequence of Fi prime or Fi such that Fi prime, the limit of Fi prime exists, and we denote it by F on omega. Since Fi prime is holomorphic, F is holomorphic on omega. And also, to show f is in the family chi of f, we need to show it's univalent. This is true because Horowitz theorem. F is also univalent. Oh, next, we make the following claim. So we want to show mu equals the magnitude of the derivative of f at the point p zeros. Probably, yeah, I'd better use a little bit different notation. Here, let's denote this f by g. To avoid some confusion. Okay, so how to prove this? Oh, wait. So equivalent, this is not so direct to prove, but we will direct show that G is onto D. And then the so why this is doable? Why this is true? Because we prove by contradiction. Suppose a point A in D is not in the image of omega and G. Then we have the following picture. This is G omega. And of course, G omega contains the origin by the assumption of the family F. And outside you have point A. Okay, now you just transform the point A to the origin. So the idea is if you take a square root map, then you expect the things inside the disk getting bigger. But here, since 0 is inside the green part, you cannot take a square root. So the idea is we transform zero to, so this is the omega plane. Transform 0 to, transform A to the origin. And of course, the green part is changed to some other part conformally. And then most importantly, 0. Let me denote this as colorful. And then 0 is mapped to, you plug in, you'll find it's negative A. Negative A. And so this is omega 1 plane. This is omega plane. Now you can take a root. So omega 2 is square root of omega 1. The reason why we keep tracking of the variable is because later on we want to compute the derivative. Okay, so here, if you take root, so this is this is 0. Okay, if you take root then you have this part, and then a becomes square root of negative a. Here, why you can take root? Because you know the green part is simply connected. Why we can take root? Because green part is simply connected. The map is automorphism, so in particular it's homomorphism in the language of topology. So connected open set is mapped to connected open set. Simply connect set is mapped to simply connect set. Okay, next we move it back. So let's omega 3 equals omega 2 minus square root negative a divided by 1 minus square negative a conjugate times omega 2. So now the color points getting back to 0, and we have the green part again. So notice that the result function omega 3 is in Mescal F. In particular, it maps P0 to 0, and it's a univalent function from omega to d. Okay, next let's compute the derivative. So we expect omega 3 is larger, or geometrically, what does that mean? That means green part gets fatter. And probably I need to draw it in a little bit accelerated way, getting bigger, getting fatter. Okay. So mathematically, we need to compute the derivative at omega 3. Oh, here I should insert a small claim. Claim G prime P0 norm is mu. Proof. We can do it by contradiction, since Fi, derivative of Fi prime. Oh, sorry. Really bad notation here. So here, take a subsequence. Let's call it Gi, such that Gi converges to G, and since Gi is holomorphic, okay. So Gi, so originally when I write Fi prime, I didn't notice that when we take a derivative, it's also the same thing. Okay, now since gi prime or gi derivative at p0, this goes to mu I, goes to mu when I goes to infinity, then you can conclude this. Okay, now let's compute derivative at omega 3. Then you will find it's a computation by the train rule times d omega 2 divided by d omega 1, omega 1 equals negative a, times d omega 1, d omega at omega equals 0, times d omega dz at z equals 0. That's why we keep tracking all the image or the color point and the notion of the complex variables in the domain. So first, recall that d omega dz is let's see. So d omega 1 omega, because omega 1 is omega minus a1 minus a bar omega. So let's take the derivative. We computed it before. Let's do it again. It will be 1 minus a bar omega plus a bar omega minus a divided by 1 minus a bar omega squared. So it's 1 minus norm a squared divided by 1 minus a bar z squared. And d omega 2 omega 1, d omega 1 is 1/2 square root omega 1, 1 over square root omega 1, and d omega 3, d omega 2, similarly is 1 minus norm a squared divided by 1 minus square root negative a bar omega 2 square. Here is omega. Okay, then when you plug in, you will find d omega 3 divided by dz evaluated at p0 is d omega 3 divided by d omega 2 evaluated at square root negative a. So it's 1 plus norm a square, 1 minus norm a square. And then for the second one, you plug in negative a, so it's 1/2 1 over square root. Note that here square root negative a always refer to the branch we take for the holomorph functions on the green part, and then times so now here you plug in 0, it's 1 minus norm a square, and then finally you have f prime p0, and then if you simplify it, do I make some mistake? Oh yeah, so here you don't, yeah, I see. Here you don't have square, therefore you can factor out 1 minus a, 1 plus a, 1 plus norm a, square divided by 1 plus square root a. Oh, sorry, here I made a mistake. It should be minus, because here 1 minus square root negative a conjugate times square root negative a. So it will be 1 minus negative square root a times square root negative a. So it will be 1 minus a, absolute value actually. Okay, so here, therefore here you can cancel out negative 1 minus square root a, 1 minus absolute value a square. So it's 1 plus norm a squared divided by 2 square root negative a f prime p0. Oh, sorry, here's g. Because the limit function is g. Okay, now if you take the norm, then you will see the norm equals this times 1 plus norm a squared divided by 2 square root norm a. Since a is different from omega, so this is well defined and it's greater than mu because this is mu. And since omega 3 is in Cal F, we get a contradiction. Okay, then we finish the proof of the Riemann mapping theorem. So I do suggest you to carry out the last few steps, how to do conformal mapping and enlarge your function by a definite quantity. So this is important. This vector. Okay, I will stop here.